Hey there, my name's Gary Sims and this is Gary Explains. Today I want to talk to you a little bit about the Rust programming language. So if you want to find out more, please let me explain. Okay, so the Rust programming language is gaining more and more momentum. It's becoming more and more popular. And I'll talk about the reasons why in a minute. But today I want to start this first video in a series about Rust. And the title here is 12 Things to Help You Learn Rust. So basically, I'm going to go over the essentials of understanding the Rust language. So what is Rust? What's all the fuss about? Well, the key thing is it's a memory safe language. The problem is that most security related flaws, so you know how Windows gets updated and Linux gets updated and Android has to get updated and iOS has to get updated and we're always receiving patches and upgrades for our software, whether it's on the desktop or on mobile, because they're generally written in C and or C++. And the problem is that most security-related flaws are caused by developers inadvertently, that means it's a bug, not intentional, inserting memory corruption bugs into their C code. Now, the problem is that C compilers trust the developer. So in C, basically, you can shoot yourself in the foot and that's perfectly okay. Now, that's a nice idea because you have complete control. You can do whatever you want. However, it does expose software to these software-related flaws. On the other hand, Rust is pedantic about memory. In fact, it's pedantic to the point of madness about memory allocation, about pointers, about how memory is used, buffer overruns. It really is memory safe to the point of madness. Now, we're going to talk about that in the second video. In this first video, I wanted to go through the basics of Rust without looking at the memory safety aspects, so that when we come to the memory safety aspects, they will actually make sense because you understand what the rest of the code is talking about, variables and loops and all this kind of stuff. So Rust is a C-like language in that it's a system language. You can write an operating system in Rust if you want to, and people are doing that and have done that. It's a compiled language, so you get a binary out the other end for Intel x86 or for ARM or whatever. There's no intermediate interpretation going along, let's say like in Java or C#. There's no interpreter. This is not like Python. So you write a program, you put it through a compiler, and you get a binary out the other end. And it also borrows some of C's syntax. You'll see things like semicolons, curly brackets, the if, else statements look very similar to what they do in C, but it's not C. That's the important thing. It borrows a lot from C, inspired by C, but it's definitely not C. So the Rust compiler is free and open source, available under 2 different licenses. It has its own build system called Cargo, which we won't be using because we don't need that just to understand the basics of Rust. It started in 2006 as a side project by a Mozilla employee. It was announced in 2010 and V1 came out in 2015. It's fast, it supports concurrency, and it works on Windows, Mac OS, Linux, ARM, x86, 64-bit, x86, embedded, and so much more. So it really is trying to become a universal language in a way that C is. Now, if you want to install Rust, just go over to rustlang.org tools installed. If you're using Linux, Mac OS, or the Windows subsystem for Linux, then you just run this curl command, which you'll find on that web page, and it will do all the stuff it needs to do, the downloading. If you're running Windows, there is a downloader, an installer to download .exe. You can run it, and it will install it, and then you get Rust C, which is the name of the compiler. However, we're not going to be using Rust C. We're going to be using the online compiler that you find in the Rust playground at play.rustlang.org, because that means we can open up a web browser and start using Rust without worrying about installing it on our system. So I said we'll be looking at 12 things. These are the 12 things, how you print things out. Mute, we'll talk about that, what it means in a minute. Shadow variables, constants, types, strings, tuples, arrays, expressions and statements, functions, loop and while, and the for loops. If you can understand all of those, you'll have a pretty good understanding of the very basics of the Rust programming language. So let's start with Println. So here we are at the Rust playground. I've zoomed up the web browser a bit so the text is quite large. I hope you can read it okay. We're going to start by writing our first program. Now I'm going to assume you have some kind of programming knowledge. maybe C, maybe Java, maybe JavaScript, Python, whatever. So these ideas will be fairly obvious to you, but this is how we do it in Rust. So the main program, where the program starts, is like C, the function called main, and FN, you'll see there's how you define a function. We'll talk more about that later. And we're just going to do the first thing, which is really easy, print line, exclamation mark. Now, I won't go into this too much, but exclamation mark means it's running a macro. Don't worry about it. Just know that when you want to print things out, you use print line, exclamation mark. And then macros is a much deeper subject we don't need to worry about now. And then we're just going to say hello. Okay, and then the thing is you need to end it with a semicolon, just like in C. So there we go, 3-line program, main, print something out, close the curly brackets. Let's go over to the run button here and run that. And there you go, it compiles it, and then here we can see down here, hello. It's done exactly what we expected it to do. Okay, so let's keep adding to this program so we can just build up a few more things. So how do you define a variable? So let's say we want a variable called x and we want to make it 7. So you say let x equal to 7. Now notice, first of all, that Rust can work out that 7's a number. So it doesn't say, oh, is that a string? Is that a Boolean? No, it is a number. So it works out automatically that you don't need to say this is an integer. Though we'll talk more about that again later in the video. And let's say y is equal to 1. There we go. 2 easy things. X equal to 7, y equal to 1. If we want to print them out, what we do is we say print line with the exclamation mark. And then we could say something like this. We could say x is, and then you put these double curly brackets like that. That means in this place here, a variable is going to go. And we could say y is. Like that, and then here outside of the string, so just like the C commands, we can put X and Y. Okay, so there we go. We're basically saying here's the string that I want to print out. When it sees the curly brackets here, it knows it needs to put in the numbers. First of all, X, and then second of all, Y. So let's give that a run. And there we go, X is 7, Y is 1. Well, that's pretty easy as well. A couple of other interesting things we can do is we could say print line, and we could say like this. What you can actually do is inside the, so we can say X is, and inside the curly brackets, we can say valx, for example, which doesn't exist in our program. It's not a variable. And we could say Y is, and we could say here, you know, whatever we like, Fred. Okay, and the reason you're doing that is you can actually now define those things in this parameter list here. So I can actually now say here, valx is equal to X and Fred is equal to Y. So what's that telling me here? It says that when it sees inside the curly brackets here, valx, it looks here to see what it should put in there. Well, it should put X in there. And when it sees Fred here, it knows it should put the value of Y. So that allows you to tie up between the variables in here, or the values you want to print out here, and the variables here. So if this gets complicated, you know, maybe you've got 10, 20 things you're printing out, and this list here goes on and on and on and on and on and on, you can actually kind of make life a bit easier there. Don't forget the semicolon at the end. Let's give this a run. There we go, X is 7, Y is 1, exactly the same thing as we would expect before. Now I want to just show you one or two more things. We can also do a print line. Now what we're going to do is we're going to set, you can use debugging information. And when you do that, rather than just put the normal curly brackets, you actually put colon, question mark, which says, please use your debugging information about this variable and print that out. And what we're going to do is I'm going to use a thing here called a tuple. We'll talk more about that in a few minutes, but you can see here that it's this 3 and this 4 in a bracket. And the reason why we're doing that is that when we run this, we'll actually see that it comes out inside with those brackets on it. Here you go, debug 3, 4 with the brackets around it, because it's showing me this is actually what's in that variable. And this can be very useful for printing out arrays, printing out vectors, and other things like that. And finally, the thing we'll show here with print line is very similar to what we did up above. We could say X, so we can say Y is, and then here, rather than putting in Fred or value Y or whatever, we say 1, and we can say X is, and then here we put 0. And what does this mean? I'm now going to put X first and then Y. Okay, so notice it's actually printing out, I want the Y first, but actually it says 1, which means it will print out this one, counting from 0, like a lot of computer stuff does. When I was at university, the computer science building, the first floor was actually floor 0. And X is 0, so it means it will print out this here and then this one here. So it picks them in an order. That's basically what it means. Do the second one, which is index 1, and then the first one, which is index 0. So let's give that a run, and then that should be it for Println. There we go. Y is 1, X is 7, exactly as we would expect. Okay, so from now on, I'm just going to kind of cut and paste the programs in and then talk about them rather than me typing them all here in kind of character by character, so we can save a bit of time and we can get into some of the other stuff we want to look at. Okay, so here's the next program. One thing here at the top, it says allow unused variables. That is a compiler directive. Because I'm doing demos here, sometimes I'll be assigning variables and not actually using them in a print statement or in a function, and that just stops compiler warnings coming up. You'll see that now quite a lot. That's all it's doing. So what we've got again is we've got our main function, and now here we're saying let x equal to 5. Well, that should be fairly obvious. We print it out, and then I say, well, actually now I'd like to change x to 6. Well, in Rust, you can't actually do that. If we run this now, the compiler will give us an error. There we go. This gives us an error saying you cannot assign twice an immutable variable. So what does that mean? Well, in Rust, all variables are immutable to start with. Immutable means you can't change, won't change. Okay, so x is equal to 5. It's actually saying, well, x is not allowed to change. So in Rust, to say this is a variable that can change, you have to say let mutable x equal to 5. And now when you come to change it here and say x is equal to 6, it will actually work. So now if we run that, we should find 5 and 6. There we go, printed on the screen, no problems. If you're ever having a variable that changes, you specifically have to tell it that it is mutable, or all variables are immutable by default. However, also Rust has the idea of what's called a shadow variable. So if on line 4 here, we see it says let y is equal to 5, and then I say let y is equal to y plus 1, notice I haven't said that y is mutable. But actually what I'm really doing is I'm redefining y. That's why I've got the let in front of it. In the past example, the previous example, I just said x is equal to 6. There was no let. So what I'm really saying is I'm now defining another variable. Oh, it's also called y. Okay, that's interesting. It's the same as what it was called before. And what's its value going to be? Well, actually, it's going to be y, which at the moment is still this value from the line above, plus 1. So what you're doing is shadowing. It means that you're using the same name and you're actually kind of like someone shadowing in a sports game. You're actually saying, well, I'm going to stick to this. So I'm sticking to y and I'm redefining it every time. And in doing so, it allows me to actually have variables that are not mutable, but I have to say let y at the beginning, or let the variable name. Okay, and then this one now, these versions of y have all disappeared. They've gone, they've been deallocated, they're no longer around. This is the kind of the master one, the current one at this point. And when we run that, of course, what we're going to get, well, it starts with 5, y plus 1 is 6 times 2, 12. So we're going to get the value of y is 12 when we run that. And we'll run that in a second, but the advantage of using this shadows is that actually you can change the type. So let ABC equal to ABC. Well, it's a very simple string. We'll talk about strings in a moment. Okay, and then we can say let ABC is equal to abc.len. Now, of course, the length is actually a number. In this case, it's going to be 3. So we're changing ABC from being a string into being a number. And when we print it out here, we're actually going to get the number 3 out. So here it shows you that shadow variables can actually change their type as you go along. Notice we've actually said let. So we're redefining it as we go to that next line. So let's run this and see what happens. And there we go, y is equal to 12, and ABC, which is now the length of ABC, is 3. Now you may be thinking, oh well, if there's mutable and immutable and then there is the shadow variables, then basically immutable variables are like constants. Well, no, constants are still something separate. So constants are not the same as just an immutable variable. Constants are not just immutable by default, they're always mutable. And you use the word const in front of it. So you can't do shadowing on a constant. You can't redefine it. You don't use the word let. You define it with const. Okay, and it may only be set to an expression. So it can't be the result of a function call. And Rust naming convention says that you should use it all uppercase. So I've got 2 here. Full HD width is 1920. and bad pi is 22/7. Now, quick two things. We can talk about this in a moment. This says it's a 32-bit unsigned variable. This says it is a 32-bit floating point variable. We'll talk more about that in a moment. But basically, this is going to be 22 divided by 7. It's going to be a constant. This is going to be 1920. And then here we just print them out. Like we've done the other things, we're printing out those two things. So let's just run that. And there we go. We've got the constant and we've got our very bad approximation of pi there. Okay, we saw that in the initial programs, the Rust compiler is able to determine that something's a number or something is a string very easy without you telling it. If you do want to tell it explicitly what you've got a whole range here of different options. You've got 8-bit bytes, 16-bit words, 32-bit words, 64-bit words, 128-bit, all signed, which you can have positive and negative numbers, unsigned 8-bit right up to unsigned 128-bit, and then I size and this should be U size is actually the size of the architecture. So if it's a 32-bit processor, that will be a 32-bit word. If it's a 64-bit processor, it will be a 64-bit. And they give you an example. Let x128. Now here, rather than just going straight to the equals like we did before, you have colon and then the type. So this is unsigned 128-bit, and then this here is 128-bit number in hexadecimal. A couple of interesting things here is that you can use this underbar anywhere in the number. I could actually put it in, here if I wanted to. It's ignored by Rust, but it means it's easy for us to start to read it. And here I've divided it up into 4 lots, so we can see this 128 bits being put together here. And then here I'm using a signed integer 64-bit, so x64. Then you've got 32-bit and 64-bit floats. So by default, all floats are 64-bit. So if I say let x is equal to 2.0, it says, oh, point must be a floating point number. So it defines it as a 64-bit one. You can explicitly say you want a 32-bit one if you want to. We can print those out, which is what we do there on line 11. You can also define a character. And then here are some more fancy characters using UTF-8, okay, the thumbs up sign, and then a Boolean there, true or false. So let's just quickly run that and we'll see all those numbers printed out. And there we have it. There's our big number, 128-bit number, 2 and 3, and then there's our characters, UTF-8 characters, and we'll talk more about that when we get to strings in a moment. Okay, so all strings in Rust are UTF-8. That basically means it's not just ASCII. You've also got support there for all the different kind of character sets that exist in the world, and of course for things like emojis. So they're a good example there of being able to put funny characters. That's certainly not part of the original ABCD of the English alphabet. So look, let howdy equal howdy with a thumbs up, and let's count the number of letters in that. 1, 2, 3, 4, 5, 6, including the thumb. So I've put this question here, is that 6 long? Well, we'll find out in a minute. So here you can print out this string. It's called a str string with a lowercase s because it's a string literal. Okay, and we can work out things like its length. Here's a function, howdy.length will show you the length of it. Howdy.isEmpty will return true or false, is that string empty. And then what we're going to do is we're going to look at the bytes. What bytes has Rust stored in its memory to do that? So you can say howdy.asBytes. There's a function there that will just show you the bytes that exist for that. And because we're just printing out that array of bytes, we're actually going to use the colon question mark there for get that debug information. We'll run that in a moment, but there's another type of string, which is strings that you can change, strings that can grow, strings that you can manipulate, and they have the type called string. So here we can say let mutable hello equal to string. Okay, so it's of the string class, and what is it where it's from? And then it's just a string literal, so it's actually a string from a str, the str, which is this kind of type here. So we're having a string, one that can be extended from a fixed string. And then what we can do is got these other functions, a whole bunch of them. You can look them up in the documentation. Push, for example, will add a W onto the end. Push str, again str because it's a string literal. World without the W. So if we add W and world onto the end, we should get hello world. And then also you can do things like inserting. So here we say insert at index 5, the comma, and so this should give us hello, comma, world. So let's run that and see. And there we have it. Is it empty? False. No, it isn't empty. But how long is it? Well, it's 9. Well, that's a bit of a shock. We thought it was 6. But actually, look, if we look at these are the ASCII codes here for howdy. But then for the emoji, look, there are 4 bytes being used. This is how UTF-8 works. So this is the 4-byte code for that particular emoji. And of course, it's starting here at 240, which shows you the 8th bit is set. So this is why it's UTF-8. Okay, and then maybe I could do a whole video on UTF-8. If you want one, please do tell me in the comments below, and I will look into doing that. Hello world, and then hello world with a comma in it because we inserted a comma. So string, when you're using the actual string type, then you can modify and extend the strings, which is something you can't do with a string literal. Okay, so in mathematics and programming languages, the idea of a tuple, you know, like a triple or a double, a tuple, which is a group of information, a collection that sticks together, and you can use them as a whole. So here we're defining a tuple, and we're saying it's made up of 4 parts: 32-bit, 64-bit, floating point, 8-bit unsigned, again 32 bits, floating point, and then you define it using those brackets. Remember, we did that way back at the beginning when I wanted to show you how printing of the debug information worked, and these now kind of can get passed around just in this variable called tup. So this is a good way of very, very quickly defining a group of things that I want to all to stick together. I'm going to pass them around together. I'm defining a second one here with some different values. I've got 2 values in it, and notice I don't define the type like I did here. This one just goes straight with the equals, and that's because the compiler, of course, can work it what it is out. We're going to print that out there on line 6. But also I can do interesting things like this. I can say let w, x, y, and z equal to tup. So that will take the 4 values here and put them into w, x, y, and z, and then I can print them out as individuals. No brackets here. I'm actually printing them out as individual variables, not a debug statement. These are just normal integers and floating points here that I'm now assigned to that. So I can basically convert a tuple back to just individual variables like that. And also I can access a tuple by a kind of an index. So 500 is tup dot 0, of course that's 0, the 0 index. 3.4 is the second tup 2 dot 1, so there it is, 3.4. Then 1 is tup dot 2, so that's 1 there. And then 2929 is tup 3, which of course is there, 2929. So we can break apart a tuple and assemble a tuple however we want. Really, really useful, especially when you're returning things from a function. You can return multiple things from a function by using a tuple. Okay, let's run that and see what happens. And here we go. The debug information has told us what the tuples look like. Here we've assigned them to w, x, y, and z. And then here they are using those individual variables that we've picked out using the indexes from the 2 different tuples there. Okay, let's have a quick look at arrays. Arrays must be all the same type, so you can't mix them between floating point and integer like we did with the tuple there, and they are of a fixed length. So let A equal to 1, 2, 3, 4, 5. That's fairly simple. Let B equal to 1, 2, 3, 4, 5, but this time defining that they are unsigned 16 bits, and actually in the process we told them it's going to be 5 long. Let C equal to 0, 5. What that does actually says I want an array that's 5 long and all of them to be 0. So a great way of initializing an array and setting an initial value. In this case, setting it all to 0. We'll print that out. That's fairly easy, what we'll see there. Let months equal January, February, March, and so on in English there. So that's an array of string literals. And now we can say let first, we're defining a variable called first, is going to be equal to A0. So A0, of course, is 1. And we can let November, let Nov equal to months 10. So the 10th month is November. Okay, and then we can print out those 2 there. So basically, arrays, fairly easy to understand. Fixed length, that's the thing to remember about about arrays. Let's run that now. And there we go. We can see those 3 arrays, the debug information. That's why it's got the square brackets around it, because we use that colon question mark. And of course, 1 and November, as we would expect. Okay, now I want to talk a bit about expressions and statements. There's another compiler directive here saying don't warn about unused brackets, unused parentheses. That's because I've done some stuff here deliberately to try to demonstrate something, and the compiler can actually moan about it a bit. So let's look at this. Let's say we've got A is equal to 3 plus 7. Well, you would know that A would be set to 10. That's fairly easy. If we say let B equal to 3 plus 7, well, that's the same thing. We've just put these brackets around it. Now, why I did that is I wanted to show you, first of all, you can put the brackets around it, but secondly, the semicolon here is nothing to do with this 3 plus 7. It's to mark the end of the statement. So this thing here is a statement until you get to a semicolon. And this thing here on the right-hand side of the equals is an expression, which in this case is 3 plus 7. Could be anything that we're trying to calculate. And Russ has got this great thing that actually you can put that same thing now in curly brackets. So remember, the semicolon here is because of the statement, but the thing here in the curly brackets is the expression. And what does that mean? That actually means you can actually do calculations using other variables inside this part here. So here it is. Look, let y equal to, open a curly bracket, just like we did here on line 7. And then what's going to happen? Well, actually, inside I'm going to define another variable called x. It's mutable, which means I can change it. And I'm going to define, I'm going to say x is equal to 3, and then x is equal to x times by 2. And then at the end of it, I'm going to say x plus 1, but notice there's no semicolon. So this is the end of my expression, and the value of the whole thing will be this very last statement, in this case x plus 1. So whatever that last line of code is inside of the block, that will be the value of the expression without a semicolon on it. So what we're going to get, 3 times 2 is 6 plus 1 is 7. And then here we've got the curly bracket again and the semicolon, which ends the statement. So this whole thing here, ending in the semicolon, is the statement. This thing inside the curly brackets here is the expression, and the value of the expression is whatever is the last line. That is what gets kind of passed on to the value of y in this case. So then if we print out y, we should get the value of 7. So let's run that and see. And there we go, the value of y is 7. So obviously this is a very powerful construct that you can do some quite interesting things with, and you get this idea that at the end of it, you return the value of the expression. Okay, so let's have a quick look at functions. So here we've got let x is equal to 5, and 5 is a function. It's got the open and close bracket after it. And so it will return a value, and then we're going to print it out in line 4. Well, what is 5? Well, 5 here is a function. That's a really interesting thing there. It's the fn, just like main. It's a function, and it returns a 32-bit integer. And what does it return? Well, 5. And notice there's no semicolon. This is one of those expressions, again, we just talked about in the last slide. And it basically says that I'm going to return 5. So you can say let x is equal to 5, and it literally will be equal to 5 because we define a function called 5. Obviously, I could have called that function, flibbity-gibbet, and it would still return 5. Okay, and then let's look here. Let x is equal to plus 1. Okay, and what's the parameter to plus 1? Well, it's the function 5, and 5, of course, returns 5. So 5 plus 1 we know is 6, but let's look at the function plus 1. It takes a parameter, which is a 32-bit number, a signed 32-bit number. It returns a 32-bit number, and again, no semicolon because this is an expression, x plus 1. So whatever x is, it will be plus 1. Of course, x plus 1, 5 plus 1 is 6. So here's two very simple functions that also incorporate the idea of an expression that we talked about in the previous example, and of course, we should get 5 and 6 when we run this. And there we go, the value of x is 5, the value of x is 6. Okay, so this is a bit of a bigger example about functions. So what we've got here, let's look at the function first of all, is odd. That basically looks at a 32-bit integer and decides if it's odd. And the way it does that is it checks the last bit because it's binary. And if the last bit is 0, then it must be an even number. If the last bit is 1, it must be an odd number. That's the way binary works and how odd and even works. And so basically it says if, this is the first time we're seeing if, so if is how you compare things. If x ampersand, single ampersand means do the bitwise binary operation of and with 1. That basically means you'll get left with the last bit. If it's equal to 0, open the curly brackets, then you return, then it's false. That's the value. It's the expression again now. So notice that. Else true. Again, no semicolons because we're evaluating expression. So basically this will tell you true or false whether something is odd or not. This function here, tuple demo, shows you that we can have a variable called t, and it's actually a tuple that contains 3 numbers, an unsigned 8-bit, an unsigned 16-bit, and an unsigned 32-bit, and I want to return something different. I'm returning a tuple that is 2 floating point numbers, a 32-bit floating point number and a 64-bit floating point number. So 3 numbers coming in, integers, 2 numbers going out, and those are floating point. And what do? Well, I basically say x is equal to 32-bit, and what is it? Well, it's the tuple, the 0 field, which I'm now casting. So here's another thing we haven't seen before, casting. I'm saying although it's an unsigned 8-bit, I want you to treat it as 32-bit, and I want you to add it to tuple index 1, also treat that as 32-bit, and of course x itself is 32-bit. So basically take this number, turn them into 32-bit floating point numbers, add them together, and that will be the return. And then again, very similar here for the y value, using tuple 2, that's this one here, as a 64-bit, and then we return it. And again, it's an expression, so you just evaluate the expression, and that's what the return value for this is here, and it's a tuple because it's got the brackets right there, no semicolon. And finally here, factorial, classic bit of recursion. Basically, I want to work out the factorial of a number. Well, it match. This is like a case statement in C. If it's 0, basically, it's a complicated way of saying if it's this, if it's this, if it's this, if it's this. So if it's 0, then expression, it resolves to 1. If it's 1, it resolves to 1. And if it's anything else, underbar there, then call factorial again. And then actually it is with number minus 1, and because this is a recursion, you've also got then the times by number, so that kind of builds up. I've got a whole video on recursion if you'd like to watch that here on this channel. Let's go up to main. What do? Is 5 and 6 odd or not, and then print that out. Pretty easy. Here's a tuple, send it into that tuple demo function, get 2 numbers out, and then finally print out the factorial of 5. So let's run that and see what happens. There we go. Is 5 odd, 6 odd, true, false? There we go, that's correct. Here's our number. What did we pass in? 6 plus 4, of course, is 10. 3 is the other one, so we're getting 10 as a floating point number, 3 is a floating point number, and the factorial of 5 is 120. Right, we've got 2 more things to look at in our 12 things we're learning about Rust today. The next one is loops. So we define a counter here called, a variable here called counter, and it's mutable, which means it can be changed. And we say, let the result equal to loop. So this is a new construct. Here you get the curly brackets to say what's gonna happen in this loop. It's here. Okay, and then you say inside this loop, which will go round and round and round, counter is equal to counter plus 1, counter plus equal to 1. If counter is equal to 10, so when counter equals 10, then break. So break will break free. I want to break free from the loop. And the value, the expression will have the value of counter times 2. Notice again, no semicolon, because we're evaluating the expression. So counter times 2, which of course will be 20. So when you have this loop, the result, because it's let result equal to loop. So the result of the loop will be an expression, which means it has a value. And that value is going to be put into the variable called result. And we're then going to print it out. Another way of doing this is with a while loop. So here we set counter to 3. We say while counter doesn't equal 0, well, print out the counter and then take 1 off it. So we should get a loop here that says 3, 2, 1, and then that's it. So that's a while loop. And the other type of loop, okay, this one, notice, doesn't have an expression. It's not evaluating to something. It's not saying let something equal to. This is just a normal loop. This is a loop which evaluates to an expression. So let's just run that. There we go. The result is 20, which of course is 10 times 2. And then here's our thing, 3, 2, 1 has been printed out like that. Okay, now the final thing we're going to look at is for loops. Now, for loops are not like C. In C, a for loop is basically a while loop with the conditions and the initialization part built into the loop. In Rust, it's an iterator, more like things you'd find, let's say, in Java or maybe in Python. So if we define an array 10, 20, 30, 40, 50, we can say for element in a.iterator, iter, okay, which basically means it will go through. So element will first of all be 10, then element will be 20, then element will be 30, then, and it basically assigns element a value from the array as it goes through the array. You don't need to type in here anything about the length of the array. You don't have to say stop when you get to the end. It just says it will do this only for the values that are inside of the array. And then we can print out the value is, and then we'll print out the, so we'll get a list here, one on each line of the values from the array. And then because again, it's an iterator, you can do the same thing. You say for number is equal to, and here we're defining a range, okay? And we're saying the range is greater than equal to 1 and less than 4, so it means 1 to 3. So it doesn't include, it's 1 less than the last number. So 1.4 means that it's going to be between 1 and 3, and .rev means do it in reverse. So what we're basically going to get is a countdown, 3, 2, 1, just like we had with that while loop, but now using a for loop, which is iterating over a range. Again, no test here if it's equal to 0, if it's greater than whatever, if it's less than whatever, add 1 to it. No, you don't have to do any of that with a for loop because an iterator, it just says I'm going to go between 1 and 3, and then the number is going to be assigned the value in each iteration of that. So let's just run that. And there we go. The value is 10, 20, 30, 40, 50, and then 3, 2, 1 as our loop goes down in reverse order there from that range 1.4, which means between 1 and 3. Okay, now we've covered the basics of Rust in terms of functions and loops and iterators and variables and mutable and immutable and so on. Now the next video that I do about Rust might not be the next video on this channel, but the next video I do about Rust will be about ownership and borrowing, which is the whole thing about memory safety and how Rust tries to stop you, and it succeeds to the most part, of actually corrupting memory and having buffer overruns and segmentation faults and all this kind of stuff, because it is really, really pedantic about who owns what bit of memory and who has access to it. So that will be in the next video, and a lot of people find this stuff pretty difficult to grasp at the beginning. Once you get a hold of it, it's like, now I get it. But at the beginning it can be like, what? So we'll tackle that in the next Rust video that I do. Okay, my name is Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do like it. And why not subscribe to the channel, especially if you want to see that next Rust video. And have you signed up to the Gary Explains newsletter? No? Then please go to GaryExplains.com and enter in your email address there. Of course, I won't use it for anything other than sending you the newsletter. Okay, that's it. I'll see you in the next one.